how quickly does a function need to converge to zero? How fast does it need to decay in order for it to have a finite amount of area underneath it? So here we have a couple of different powers of 1 over x. We have 1 over x to the 1/2 right there. So that's going to decay pretty slowly. We have 1 over x, which decays a little bit faster. And if we have 1 over x squared goes pretty quickly. So 1 over x squared will decay pretty quickly. So how fast does a function need to converge in order for it to have a finite amount of area underneath it? Let's study this. We will integrate from 1 to infinity the function 1 over x to the p, where we're going to play around with different values of p to figure out which ones converge and which ones diverge. So the way that we're going to integrate this is by taking a limit as, let's call it alpha, goes to positive infinity, and integrate up to that alpha. And I'm going to go ahead and write this as x to the minus p. Now, you can't immediately jump into a power rule because it depends on the values of p. If p is equal to 1, then this is 1 over x. And the integral of that is a natural log. So let's talk about this case first. The integral from 1 to alpha of x to the minus 1 is going to be a natural log of the absolute value of x, but I'm integrating over the positives, so I don't need the absolute value. And we'll take that antiderivative between 1 and alpha. This becomes natural log alpha minus the natural log of 1, but that's 0. So we end up with just natural log of alpha. So when we look at the limit as alpha goes to infinity of the natural log of alpha, remember your natural log function is monotonically increasing. And even though it slows down, eventually it's unbounded. So this becomes infinity. So underneath the 1 over x function, there is an infinite amount of area. So this function here does not decay fast enough. The integral diverges. There's an infinite amount of area underneath it. So now that we've dealt with the case where p is equal to 1, let's look at the case where p is not equal to 1. If p is not equal to 1, we can use a power rule. So the integral from 1 to alpha x to the minus p is going to be x to the minus p plus 1 divided by minus p plus 1. And we evaluate that antiderivative between 1 and alpha. So I'm just going to rewrite some things here. I'll write this as x to the 1 minus p over 1 minus p. And then evaluating at alpha and then subtracting the value at 1, we have alpha to the 1 minus p over 1 minus p minus 1 minus p 1 minus p. Okay, let's get a common denominator and pull that denominator out. So I'm dividing by 1 minus p, and I'm left with alpha to the 1 minus p minus a 1, because 1 to the anything is just going to be a 1, right? As long as that p is not 1, but that's the subcase that we're involved in. We know that p is not equal to 1, which also means that this denominator is not going to be 0. So everything here makes sense. Okay, and let's rewrite this one more time as 1 over 1 minus p times 1 over alpha p minus 1 minus 1. Okay, because it's a little bit more obvious to me about what happens to this as alpha goes to infinity. So let's finally look at this limit. The limit as alpha goes to infinity of 1 over 1 minus p times 1 over alpha to the power of p minus 1 minus 1. All right, now let's look at a couple different p-values. We know that p is not equal to 1. So if p is greater than 1, right, let me write this in blue. If p is greater than 1, then that means p minus 1 is going to be a positive number, which keeps that alpha in the denominator of this fraction. And as alpha gets larger and larger, this fraction will decay to 0. So if that fraction decays to 0, then this term approaches the value of minus 1. So when p is greater than 1, this limit is equal to minus 1 over 1 minus p, which we can write as 1 over p minus 1. So that's pretty neat. If p is greater than 1, then the integral converges to the value of 1 over p minus 1. Let's look at that over here. And let's clean up my picture. So here we have one of those examples. Let's look at 1 over x squared, right? The p-value there is 2. 2 is greater than 1. So this integral is going to converge. It will have a finite amount of area underneath it. And the area is going to be 1 over p minus 1. So the area underneath the curve 1 divided by x squared is finite and is equal to 1. All right, let's look at our other case. When p is less than 1. When p is less than 1, then p minus 1 is going to be a negative number. And if that's a negative number, it is going to move that alpha up into your numerator. And if your alpha is in your numerator, and you send alpha to infinity, this term is going to approach the value of infinity. So here we diverge. So our integral does not exist. So let's write a summary sentence. The curve 1 over x to the p has finite area if p is greater than 1. So think 1 over x squared or 1 over x cubed, or even 1 over x to the 1.001. As long as that power is greater than 1, it's going to converge fast enough to have a finite amount of area underneath it. And its value is equal to 1 over p minus 1. It has an infinite amount of area if p is less than 1. So think, or in fact, p is less than or equal to 1, because we showed the equals to 1 case has an infinite amount of area underneath it as well. So if p is less than or equal to 1, we have an infinite amount of area, so the integral diverges.